Okay, in this lesson I want to talk about displacement. In our first lesson we talked about a quantity called position, which is just a way of measuring the location of something. What do? Well, if it's moving in one dimension, we draw some kind of number line like this. If it's moving horizontally, it will be a horizontal number line. If it's only moving vertically, you could have a vertical number line. If it's only moving along some diagonal, you could have a diagonal number line. So we talked about position. So there, I've defined a few things. My choice of where 0 is really up to me. My choice of where 1 is really up to me. And depending on my units, we'll maybe assume this represents 1 meter. But once I've defined where 0 is and where 1 is, then I have no more choice. That has to be 2, has to be 3, has to be 4, etc. So these are called position. They'll have the same units as distance: meters, kilometers, centimeters, whatever. The standard unit, though, is meters. The rest are all defined as that. A centimeter is defined as being 1/100th of a meter. A kilometer is defined as being 1,000 meters. In this class I want to talk about a quantity called displacement. And we'll start with just a definition. The definition is that the change in position of an object is called displacement. Okay? Displacement has a magnitude and a direction and is therefore what we call a vector quantity. So when we're given the displacement of an object, we should know, not only how far it has moved, but in what direction. A couple of things we've mentioned before. The Greek letter delta means a change in some variable, and the letter S is used to denote displacement. So the way mathematically in algebra we would write the definition for displacement, we would say displacement S is equal to the change in position. Okay, position, maybe we could use X. Why would I use X for position here? Because maybe this is an X-axis. Okay, so that is that is the nice concise way we have of defining displacement using algebra. Up here is our kind of defining displacement using English. You can see why algebra is a much more efficient and concise way. So if I take Plas-Johnson here and I say Plas-Johnson starts over here, I'm going to shrink him down so that there's no doubt. So the initial position here on the x-axis, I'm going to call it initial position. Plas-Johnson starts there with initial position. Well, you can see his initial position here is 4. And then Plas-Johnson moves, say, this direction over here to position -3. So I might say his final position is -3. And I want to describe the displacement of Plas-Johnson. Okay? So the displacement, we'll come back to displacement in a moment. One thing I will point out that the numbers are increasing here as I go to the right. So this system is what we would call a right positive system. So I want to define displacement. Well, we know the displacement is equal to the change in position. And the change in any variable is equal to its final value minus its initial value. So in this case, the final value would be -3. The initial value here would be 4. So the change in positions, -3 subtract 4, that's -7. That's the displacement. If the units are meters, I should put those in there, -7 meters. So what does that mean? Remember, a vector quantity, it has a magnitude and a direction. Well, the magnitude is the 7. That's telling me how far it moved. The direction is negative. Remember, we said this is a right positive system, meaning the numbers are increasing as I move right. So a displacement of -7 means that Plas-Johnson has moved 7 units in the negative direction, which in this case means to the left. Okay, 7 units to the left. So that's how we define displacement. The other thing we spoke about last day is two-dimensional movement. An object can move around, it doesn't have to move in a straight line. Something could move in a circular way or kind of sweep in a curve or, anything at all. Or it could make a couple of movements, one to the left and down. So if I take Freddie Hubbard here and I, kind of describe his motion. Again, I'm going to shrink Freddie right down until he's almost a dot. And I'm going to place Freddie Hubbard over here at this position. In this case, I might define position with the letter P, so I might say Freddie Hubbard's initial position is equal to, let me just rewrite that. His initial position, PI, is equal to, well, it's 3 units to the right and 4 up on my coordinate system. You know, I've just chosen this coordinate system. Somebody else might decide that their coordinate system is here, in which case his position would be 2 units to the right and 2 up from the origin. But I've decided that this is my coordinate system. I've chosen where my 0 point is, my origin. This is 1 unit to the right, that's 1 unit up. Once I've chosen those couple of things, everything else it just follows along logically. A couple of things about the system, of course. This is positive to the right because the numbers are increasing going right, and positive up. And that's what we're kind of used to. So we'd call this a right positive, up positive system. So Freddie Hubbard's initial position is 3. We would describe this in physics as 3I hat plus 4J hat. And again, the units here would be maybe meters, depending on the context of the question. And then suppose Freddie Hubbard decided to move, and maybe he moves, you know, in some kind of squiggly way, you know, a jazzy way down here, down to this position down here, and maybe he finishes up there. We might say that Freddie Hubbard's final position is equal to, well, that would be -2, comma -4. The way we'd write that is -2I hat subtract 4J hat, whatever the units are. You know, maybe we'll just stick them in as meters. So position. So I want to find Freddie Hubbard's displacement, and we define displacement as the change in position. I'm using P for position here because we've got X and Y coordinates. And the change in any variable is its final value minus its initial value. That's how we establish the change in a variable. So the final value, his final position, is -2I hat subtract 4J hat. His initial value was 3I hat plus 4J hat, but I'm subtracting that value. So what I'll be doing here is I'm going to be subtracting the 3I hat and subtracting the 4J hat, and then I can conclude that the displacement of Freddie Hubbard over this series of movements, his displacement was -2 subtract 3, well that's -5I hat, -4 subtract 4, that's -8J hat. So that means he's ultimately had a change to the left of 5 units and down 8 units. So whatever happened, this is saying ultimately there has been change in this way. He started at 3I hat plus 4J hat, which is there. A change in position, a displacement, -5 hat minus 8J hat. That means he's moved 5 units to the left and 8 units down overall. Okay? And that is displacement, and it's a second important quantity on our course. The third thing we'll be talking about in our next lesson is something called average velocity. Okay? So displacement, the change in position. Remember, it's a vector quantity since it has both magnitude and direction. Okay? The units in this case, we might say, are meters.